Thank you very much, Chris. So welcome back everyone from lunch. We're going to start our second tutorial session at NIPS 2014. The tutorial is going to be given by Professor Thomas Richardson, who is a professor and actually chair of the statistics department at the University of Washington, Seattle. I've known Thomas for quite a long time. He got his PhD from CMU in logic, computation, and methodology, which is a very interesting sounding PhD department. And he has a lot of honors and fellowships, including being, for example, a fellow of the Center for Advanced Studies in the Behavioral Sciences at Stanford, and is also a Fulbright Fellowship recipient. Thomas is he's been working in machine learning and statistics, graphical models, and causal models for quite a long time. And I think that he is probably one of the core and most important researchers in this area, and has done, in fact, fundamental work in the area of graphical models. Normally, when we at NIPS think of graphical models, we think, for example, of how one can do inference more quickly in a given graphical model. Thomas is, I think, one of the rare researchers who is really a graphical model theorist who not only works on strategies for computation in graphical models, but also new strategies, new semantics of graphical models. For example, a form of graph that has bidirectional edges that corresponds to confounding causal influences on the two variables that are so connected. In fact, causal modeling, as probably many of you realize, has become and is becoming more important in the area of machine learning. And so I've been hoping to get Thomas here at NIPS in some context or another for a long time, and we finally have the opportunity for him to come in a perfect context, which is a tutorial, because of his influence and prominence in the field. So without any further ado, if you could all please join me in welcoming Thomas Richardson to NIPS.
Okay, thank you very much for the invitation. It's a great honor. Before I start, I should say I realized that there was another tutorial on causal modeling last year, given by Judeo Pearl himself, and so I will be very interested to see if people who are if there are anybody who was at both of them, sort of see overlaps and can contrast these two. I should also note that I've added the word non-parametric here, and I'll say a little bit more about that as things move forwards. So the plan is that I will cover the following five topics. I'll start out talking about potential outcomes, also known as counterfactuals. And this is a method of thinking about causality that has a very long history, which I'll briefly review. I'll then talk about ways of combining graphs and potential outcomes and describe a new way of putting together a graph, DAGs, or Bayesian networks, some of you may be familiar with potential outcomes. And then I'll talk a little bit about, change topic a little bit and talk about identification of intervention distributions in DAGs with hidden variables. And there'll be some themes that will continue, but basically the element of potential outcomes will sort of taper off there. And then that will lead on, if we have time, I'll talk about how some of those ideas go forward to think about learning structure with hidden variables, and most recently, my current area of research, nested Markov models, which are graphical models based on generalizations of conditional independence. So non-parametric constraints that are not conditional independence constraints, but are similar in many respects. Okay, so let's first talk about potential outcomes. I'm going to use the word potential outcome and counterfactual synonymously. Sometimes people make slight philosophical distinctions between them, but I'm going to use these two terms to mean the same thing. So the overview of this part, I'm going to talk about randomized experiments, and then we'll, those are sort of fairly easy to understand, and then we'll talk about observational studies, and then I'll talk about instrumental variables, which in some ways can be seen as linking these two previous kinds of study together. So people have been interested in causation for a long time. Here we've got Democritus saying he would rather discover a single cause than be king of Persia. Jump forwards to the 18th century. David Hume gives this definition. He says, we may define a cause to be an object followed by another, and where all the objects similar to the first are followed by objects similar to the second. So in his sort of 18th century language, he's trying to say that if we have a causal relationship, then there should be some form of association. But he then adds in this extra caveat, which is very important, saying where if the first object had not been, the second never had existed. So he's acknowledging that a simple association is not enough for there to be a causal relationship. We also want to have it that if the if the cause is not just enough for every time we see the first thing happening, then we also see the second. It also has to be the case that if the first had not happened, the second also would not have happened. And just in case there are any philosophers of science here, this is not, Hume is famous for 3 causal theories. This is not one of them. This falls into his unpublished tech reports category. So jump forward to the 20th century, and people were thinking about agricultural field trials. They want to know which seed varieties produce or cause the greatest yield, or which types of fertilizer cause the greatest yield. And they face this problem that you can't get 2 bits of field that are exactly the same, and it will vary from year to year, and weather conditions will vary. And Jerzy Neyman, in his master's thesis, written in Polish in 1923, comes up with this formulation for this problem. He says, if we want to compare V different varieties on M plots, we're going to consider a set of numbers, which we're just going to think of as being fixed, a matrix of fixed numbers, where Uij is the crop yield that would be observed if variety I were planted in plot J. So for each one of our plots, there are V different varieties that we might choose to plant in that plot. Due to logistic constraints, physical constraints, we can only plant one variety in a given plot in any given growing season. So consequently, we're only ever going to see one number in each column. We'll only get to see one number. If we decide to plant the first variety in the first plot, we get to see this number. If we plant the Vth variety, we get to see this number. But conceptually, we're going to imagine this set of numbers as existing, even though we're not going to ever get to see all of them. And as you can see, this has a firm tie-in to missing data, which I will continue to exploit as we move forwards. Okay, so now to make things simpler, I'm now going to just consider a simple setting where I have a binary treatment taking values 1 and 0, drug or placebo, and binary outcome. And for each patient, the outcome is either good or bad, recovery being 1, die being 0. Okay, so we've gone from plots in a field to patients, and instead of kilograms of wheat as our outcome, we've got whether you live or die. Okay, so we can now, if we think about that matrix, we want to now have 2 different variables for each subject. We want to have y of x equals 0, which is the value of y that would be observed for a given unit if they were assigned x equals 0, and y of x equals 1 is the value that would be assigned, would be observed, it's the outcome that would be observed if that unit were given the drug. Okay? These are 2 different random variables defined for every person in our population. They're not different realizations of the same random variable. Probabilists sometimes get confused by this notation. And just to keep things short, I'll sometimes write y of xi as an abbreviation for y of x equals I. So this model was popularized by Rubin in 1974, but the Neyman's ideas sort of were continued and developed through the experimental design literature, and so it's often called sometimes it's called the Rubin causal model. It should probably, Neyman Rubin causal model is probably the most accurate. So here's a sort of very simple setup. Supposing I've got 5 subjects in my very little study with 5 subjects. Here, conceptually, is this matrix of numbers. And the simplest idea, sort of obvious from the setup, is that if you are actually assigned to treatment X, then we get to observe the potential outcome corresponding to the treatment you're assigned to. So we have this tautology. An individual who has x equals x, their observed response y is equal to the response y of x that would be observed had x been x, which is perhaps most easily expressed just by this picture. So here's our little population. Here are their potential outcomes. The first person, we have now assigned them to get the drug, and then we then go to this column, the y of x equals 1 column, to find out what their outcome is. So this person lives. Okay, the next guy, second person, is assigned to the placebo. We go over to this column and find out that unfortunately that person is going to die. Okay? And so this is our observed data. So the observed data is obtained in this very simple fashion from the potential outcomes by simply assigning each person to a particular treatment level, and then the observed outcome then corresponds to the particular potential outcome that the person was assigned to. Okay. It's also sometimes useful to give names in a simple case like this, give names to these different types. So somebody who has a bad outcome, regardless of what they get assigned to, we say is of type never recover. Person who has a good outcome only when they get the drug is of type helped, hurt, and always recover, being the 4 different types that we can have. So key distinction here is that X is the treatment a given patient actually gets. And that could be the result of flipping a coin in a randomized experiment, or it could be the result of a doctor looking long and hard at the patient and trying to decide what they thought was best for the person, or it could be the patient's choice themselves. Y is the observed response for a given patient. Okay, that's what we actually see. So this capital X and capital Y are the things we actually get to observe. Y of X is a response that would be observed for a given patient if, possibly counter to fact, they received X equals X. Okay, so this is what we actually get to see. We don't never get to see this matrix of numbers. At least in general, we don't get to see this matrix of numbers unless you're in a happy setting where you're doing a psychology experiment where you give people a shot of vodka 1 week and then take their reaction times, and then you bring them back a week later and give them a shot of water, and then under reasonable assumptions you might suppose that you're getting to see both entries here. But the context I'm going to look at, we're going to suppose we face this fundamental problem that we can only see the outcome under one of these treatments. Okay? So, for example, this first guy here, we will know that they got the treatment, we will know that they had a good outcome, but we won't know whether or not they were of type helped or whether they're of type always recover. Okay? Likewise for the others. So here I'm explicitly making the analogy to missing data. Okay, so you might think that we haven't assumed anything. This looks completely non-parametric, but of course we have done some things in that we're supposing that these are well defined. And you might think, well, what could go wrong with that? Well, we're supposing in particular that there is one specific outcome corresponding to what happens to you when you get the drug or the placebo, so there aren't sort of different ways that you could get the drug. And we're also supposing that a particular subject's outcome only depends on what they receive. Okay, so we're supposing we're not it's not something like an Ebola vaccine where if all of your friends and everyone that you're in contact with is vaccinated, then it might not matter whether or not you're vaccinated, but if not, then your outcome might depend on whether or not your friends were vaccinated. This sometimes gets called the stable unit treatment value assumption, or no interference. Okay, so we're supposing that these things are well defined. I just want to make clear that that is an assumption of a certain type. Okay, so there are many quantities that we might be interested in, but an obvious one to be interested in is the average causal effect, which in this simple setting is just the difference between the proportion of people that are of type helped and the proportion of people that are of type hurt. Okay? So you can think about this as this is the difference in the proportion of people that would recover if everyone were treated versus if nobody were treated. And this lives between -1 and 1, being a difference of 2 probabilities in this setting. So if we randomize treatment so that X, the assigned treatment, is independent of each of these potential outcomes, then just via that independence we get this, that the probability of having positive outcome if you were to get X equals I is equal to the probability that you would have a positive outcome if you were to get x equals I among people that actually did get x equals I. So this is using that independence, using the independence up here. And then using our tautology, using the tautology that we saw, we can then rewrite this in terms of the observed distribution. Okay, so we've got something over here which, if you looked at it at first sight, if we hadn't done any randomization, you would have to know all of the entries in that column, including the entries that have the question marks. And we've now identified it by this observed quantity. Okay? And so then just by the same logic, we can then get at the average causal effect as just the difference in the expectation conditional on x equals 1 and the expectation conditional on x equals 0. Okay. So let's start. I want to think about this a little bit more geometrically for reasons that will become clear in a moment. So just to be clear, what we've seen so far is that if I have this randomization, then this quantity, the average causal effect, is identified. Okay, so let's think about, we can think about this as a two-way table. Under randomization, we can think of it as a two-way table with, here we've got our 4 types of patient: never recover, hurt, helped, and always recover. And under randomization, we get to observe the row sums from this table in the treatment arm, and we get to observe the column sums in the control arm. Okay? So we could rewrite it like this. So these are the quantities describing our population. In general, we won't get to know those, but we do get to know the row sums and the column sums. So those of you that have seen ecological inference problems, you will recognize this. So we could try to, given that we know these margins, we can see what we can infer about these quantities here. Okay? So we obviously, since we know this sum and this sum, we can obviously find the difference between the proportion helped and hurt. That's the average causal effect. That's the logic that we just saw on a previous slide. But what more can we say about these 4 quantities here? So if we think about it, we can see we've got sort of 3 unknowns, because these 4 quantities have to sum to 1. We've got 3 unknowns, but we've only really got 2 pieces of information. Okay? So I'm going to look at it like this. Think about this. This is the set of all possible distributions we could have over those 4 types. And then this is our observed data, the observed data consisting of the recovery rate in the control arm and the recovery rate in the treatment arm, which are equal to these by randomization. Okay? So this is just a very simple map that takes us from these proportions to these row and column sums. So the first and most obvious thing we can see is that the map is onto. So there's no way that I could give you a recovery rate in the control arm and recovery rate in the treatment arm, and you could say, that couldn't possibly have arisen. With just sort of common sense, we can see that there's no restriction at all here in terms of what pairs of observable distributions we could observe. Now, the second thing we could ask is, okay, so if I give you an observed distribution here, what can you tell me about the set of distributions over those 4 types that could possibly have given rise to it? Okay, and as I said, we can see this isn't going to be a single point because we don't have, we've got an underdetermined system. We've got 3 unknowns and only 2 pieces of information. Okay? So this is our identification problem, is that we want to know everything we can about this, but we're just given this. Okay? And the observed, under randomization, the observed joint just puts 2 restrictions, which are basically the row sum and the column sums. Okay? So this is the graphical picture that tells us what's going on. So here is a 3-dimensional simplex. I'm going to make use of this such simplices frequently in the talk, and I'll always label them the same way. So this axis here will be the proportion helped. This axis will be the proportion hurt. The axis on the back will be the proportion always recover. And then, given that I give you a point in the simplex, you can find the proportion never recovered by just doing 1 minus the 3 that you do know. So if I tell you the proportion recovering under control, then that's equivalent to knowing the percentage hurt plus percentage always recover. In this particular plot, that's 0.3. That gives me this yellow plane. If I tell you the proportion that recover under treatment, then that's equivalent to telling you the proportion help plus proportion always recover, which gives me this blue plane here. So given that you've given me both these pieces of information, they both pertain to the same population, I then know that the unknown population distribution has to lie somewhere on the intersection of these two planes, so it has to lie somewhere on this line segment. Okay? And that line segment, sort of trivial if we think about it, we can see it will correspond to a set of points where the average causal effect, the difference between the proportion helped and hurt, will be constant. But we can see that at the same time, it only places bounds on the proportion helped, bounds on each one of these different proportions. Helped, hurt, always recover, and never recover. Okay, and we could, if we wish to, we could describe this line segment here via, we could parameterize it in this way, and the extreme points are given by Frechet inequalities. Okay, so what have we done now? To recap, I've described to you everything that we can know about the four unknown types, the distribution of those four unknown types, given data from a randomized experiment. Okay? And we see that the distribution is not identified, but it is identified up to this one-dimensional space. Okay, so now let's step back for a second. Suppose now that I give you some data, and it's not from a randomized experiment. Suppose that it's just data that fell off the back of a lorry. I just tell you we have this, we observed this group of people. If you want, you could think of these as just being 20 people, because people tend to work better with numbers than with proportions. We have these 20 people, and 7 of them took the placebo and died, 3 took the placebo and lived, and so on. Okay? Now, we're now not assuming that things are randomized. So now, given that under these circumstances, what's the largest proportion of people that could be of type helped? So if we think about this, so think like a lawyer now, okay? Think like a lawyer. So you're trying to argue that this drug is really good. Okay, so these guys down here, they got the placebo and they lived. We can't really claim that they were helped by the drug, right? They were still alive even though they got the placebo. These people up here, we're also going to have a hard time claiming were helped by the drug because they got it and they're dead. Okay? But all of these people, we could try to claim that all of these people would still be alive if only they got the drug, and that all of these people here clearly would be dead if they hadn't had the drug. So if we're trying to make the drug look as good as possible, we're going to claim that 13 out of 20, 0.65, are helped. Okay? Again, thinking in the same mindset of trying to make the drug look good, how many people are hurt? How many people do we think are hurt here? So the question arises, do we have to admit that anyone was hurt? So these people up here, the ones that got our miracle drug and they're dead, what are we going to claim about them? We're going to claim that obviously they were just hopeless. They got our miracle drug, they're dead, it wouldn't have mattered what we had done. There was nothing we could do for them. So these are all, we're going to claim all these people are of type never recover, and likely the people down here who didn't get our drug and are still alive, we're going to claim that they're all of type always recover. Okay? So we're going to claim that there's no one of type hurt. Okay? So that gives us our upper bound on the proportion, on the average causal effect. So our upper bound here is going to be 0.65 minus 0, 0.65. The same logic, just turning it around and now thinking like a lawyer for the plaintiff, we can likewise argue that, in fact, all of these people were hurt, these people are of type never recover, and these people are of type always recover. So turning it around, we can get that the minimum value of the average causal effect is minus 0.35. Okay? So just to note, this little example is set up so we have exactly the same conditional probabilities that we had in our previous setup. in the randomized experiment I talked about earlier. So this is a sort of good news, bad news story. The good news is we have learned something about the average causal effect from this data, even though it wasn't from a randomized experiment. Because originally we started off with -1 to 1, but the bad news is that our bounds straddle 0. Okay, we can't tell whether or not the drug is doing anything, is positive or is having good effect, a bad effect, or no effect. And that will always hold, right? In general, we'll always have these bounds. So, suppose that we obsessed about this a little bit more and said, what further information could we obtain? Okay, so we've already worked out that we're never going to be able to, just if I give you the data from this observational study without further assumptions or other information coming from somewhere, I'm not going to be able to bound the average causal effect away from 0. But what further information can we obtain? Okay. You might think, well, why do we care? So bear with me, and I will show you subsequently why we're thinking about this particular setting, because it's going to turn out to be useful subsequently. So if we have an observational study, we can relate, we now have the following relationship between the observed and the counterfactual. So things on the left are just equal to the things on the right. So in our observational study, the people, for example, who have x equals 0 and y equals 0, they are the people who chose x equals 0 and are of type never recover, and the people who chose x equals 0, and these are slightly more tragic, these are the people that are of type helped. Okay? And likewise for all of these. Okay? We could also write this, so this is just write it in terms of these types, just to remind you what they are. We could also write it in terms of the potential outcomes. These notations are equivalent. Okay, if we think about this, we realize this is just a projection, another projection. We've got these points over here that live in this. We've got a distribution over three binary random variables. This is a 7-dimensional simplex. And we're just projecting down to our observed two-way table, which lives in a 3-dimensional simplex. Okay, so those of you that are good at doing moderate-sized convex polytopes in your head will sort of see what the image of this thing is, but we're going to go through and just describe what it is. It's not very hard to see, but it is a little more complicated than you might immediately imagine. Okay, so the first thing is that, again, as before, this map is clearly surjective. We can get any joint distribution coming out from here. So now turning to the second question, what can we learn about the counterfactual distributions, specifically the distribution over types, if I give you a particular observed distribution? Okay, so we've already seen, in some sense, the punchline's already been taken away. We know that we're not going to be able to bound the average causal effect away from 0, but still we're going to be bloody-minded and try to work out what can we learn here. Okay, so here we're given this, and we want to learn this, and this is not from a randomized experiment. Okay, well, it turns out we can get bounds on these joint probabilities, and we can just see we can see these bounds, these upper bounds, just by staring at the table up there. Okay? So if I tell you the numbers on the column on the left, and then you're trying to upper bound proportion helped, so if I take the number here and the number here, you can see that that has to be an upper bound on the proportion helped. Why is that? Well, if we look at the quantities on the right-hand side of the table, we can see everyone of type helped either shows up on this line or shows up on this line. Okay? So consequently, the sum of these two probabilities gives me an upper bound on the proportion helped. Okay? Because everyone who is of type helped is accounted for in these two probabilities. There may be some other people in there, but there's no other people of type helped anywhere else on the right-hand side. Okay? And likewise, the same logic, we can get an upper bound on the proportion hurt, we can upper bound on the proportion never recover, and the proportion always recover. Though the upper bounds on these last two simplify just to be these marginal probabilities of y. But there's some more information we can also get bounds on the marginal probabilities. So the marginal probability y of x 0, this is the proportion hurt plus the proportion always recover. And this marginal probability is the proportion help plus proportion always recover. So we can see, we can get upper and lower bounds on these. So let's just go through one of them. If we look at this down here, this quantity is the proportion helped plus proportion always recover. This quantity here is a lower bound on that. Well, how is that? Well, we can see that everyone who's on this row is of type helped or always recover. So clearly that's a lower bound on the proportion of type helped or always recover. Likewise, we can see that everyone on this row is not of type helped or always recover. So 1 minus that is an upper bound on the proportion helped plus always recover. So recapping, we've now got 6 pairs of upper and lower bounds. We've got 4 pairs on the joint probabilities, and we've got 2 pairs on the marginal probabilities. Okay? So we can now put all of this together back into our simplex plot. Okay, so here's our simplex, and I'm going to take the same observed data we had before and just add in all of the upper bounds. Okay, so you can see the lower bounds on the 4. These are the trivial lower bounds on the 4 proportions: hurt, helped, always recover, and never recover is the front of the simplex that I have removed in order for us to see what's going on. So here's the upper bound for never recover. Here's the upper bound for helped. Here's the upper bound for hurt. Here's the upper bound for always recover. And then I also have upper and lower bounds on these marginal probabilities. So now I'm putting in upper and lower bounds on always recover plus hurt, and on always recover plus helped. Okay, which gives me, so we've now worked out, if you were following which are upper and lower bounds, we've now worked out that our unknown population distribution has to live somewhere inside this little cell, little polytope defined by these 6 pairs of planes. So if we were to just draw exactly what that looks like, it looks like this. Okay? And we can confirm, if we wish to, the bad news that we're not going to be able to bound the average causal effect away from 0 by just taking this picture and looking at it from underneath, taking this 3D plot and looking at it from underneath. We see this is the projection onto that face of that polytope, and we can see, sure enough, this is one point, and this is the other point. This is the point where the average causal effect is plus 0.65. This is where it's minus 0.35. Okay, so it straddles the 45-degree line. So we've confirmed the bad news now in an elaborate and complicated way. Okay? So I still haven't yet told you why this is helpful, but I will show you that in just a second. But for now, I just want you to see this picture, that basically, given that I give you data from an observational study, I can now come up with this shape describing exactly the set of distributions over those 4 types that are compatible with our observed data. Okay, so here's the summary so far, and I'm now going to draw the first graph. There'll be more graphs as we go on, but here are 2 graphs just to sort of tie things in temporarily now. Okay, so here, think about this graph as being a randomized study, we associated this with these 2 marginal independencies, and I said that under those circumstances, these marginal probabilities were identified, but we saw that the joint probabilities were not identified, but lived in a one-dimensional set. Okay? In an observational study with confounding, so think about this H as being these confounding variables. So, people, this is something like the people that are choosing to take treatment are not the same as the people that are choosing not to take treatment. Then at least one of these fails to hold. We then have that these joint probabilities, the joint probabilities continue to be not identified, but in addition, the Meisel probabilities are also not identified. Okay, so far so good. So now I'm going to make good on this promise of telling you why I went through the hassle of showing you, working out this apparently very long-winded way of coming to this negative conclusion. So the idea is the following. Is it possible that I could combine two observational studies? So supposing I have two observational studies, and say in one observational study, it was Dr. Smith was choosing which people got treated, and in the other study, Dr. Jones was deciding who got treated, and suppose that patients were randomly sent to those two doctors. Okay? Under those circumstances, we might be able to put together the information from two different observational studies in order to get information about the average causal effect. Okay? So here's an example, slightly different example, but similar one, relating to a randomized experiment, but a randomized experiment in which not everybody did what they were told. So in this randomized experiment, Z represents what people were asked to do, so that it was a double-blind experiment. Certain people were given bottles of placebo pills, other people were given bottles of active treatment, but then the patients were monitored. This is partly because the pills had side effects, and in fact, the people were sufficiently worried about whether or not the side effects from the active treatment might be leading to people not taking the pills as often as they should, and that leading to the drug being less effective, that they even engineered the placebo to also give slight side effects. They weren't horrible side effects, should be said, it was just gas. Okay? But they were monitoring whether or not people were taking the pills. In fact, I'm simplifying the example because compliance was monitored as how often you were taking the pill over a period of a month. Pearl used this example and dichotomized that. So that's why I'm saying X here represents whether or not people took more than a certain amount of the drug. And then Y is then the patient's health outcome, whether or not they were able to lower their cholesterol. Okay, so notice that if you were in the placebo arm, there was no way you could get hold of the active treatment. So these zeros are structural. But amongst people in the treatment arm, some of them decided not to take the drug that they were asked to take. So some people who were assigned to take the drug actually ended up not taking it. Okay? So what we're going to do is we're going to analyze this. We're going to analyze the top data as if that was one observational study. Then we're going to analyze the bottom set as if that were another observational study. Okay, so here we are. We've now constructed the same polytope that we did before, once for the Z equals 0 arm, and once for the Z equals 1 arm. So for the Z equals 0 arm, we just get this little plane. That's because the Z equals 0 arm was pretty boring, because basically everybody did what they were told. But then for the Z equals 1 arm, we have this more complicated structure. Okay, so now our basic idea will be to say, well, if it's a double-blind experiment, we might reasonably suppose that which arm you're assigned to is not having any effect on your outcome unless you actually take the treatment. Okay. So what we're going to do is we are going to put together the information from these two arms. So the first arm tells us that the proportion of these four types have to live somewhere in here. The other arm tells they have to live somewhere in there. So when we put together these two arms, then under the assumption basically that Z only has a direct effect on Y through X, does not have a direct effect on Y except through X, we can infer that the unknown population distribution has to live in the intersection of these two polytopes, okay, which I've now drawn over here on the right. Okay, so if we took these two polytopes and then intersected them, we'd then end up with this little plane that we've got over here on the right. Okay. And now we can see that we have finally got a payoff for having worked out what these polytopes were. Okay. If we project, just look at the thing from underneath, we can now see that we still don't know the average causal effect. The average causal effect is still not identified, but we can see good news that even though we had a fair amount of non-compliance, the average causal effect is bounded away from 0. Okay? So our upper and lower bounds, the upper bound's 0.78, the lower bound's 0.39. Okay? So let's just think about this 1 second. There's a little geometric argument that was used here, and it's worth just nailing exactly what it was. So notice that if I project, when I project each one of these arms separately, I get bounds that straddle 0. When I put the two together, I get bounds that don't straddle 0. And this is because the operation of taking the intersection and projecting do not commute. Okay? So if I first take the intersections, and then I project, I get these nice sharp bounds, whereas if I were to project and then take the intersection, I would get bounds that would straddle 0. Okay, so here's the picture thus far. We've done all this work, and we've got these two, we've got this upper and lower bound. Now I'm going to come back to this because up until now, the statisticians amongst you will have noticed that all I've done is plugged in the empirical distribution as if it were the population distribution. Okay? It's a little bit naughty because we didn't really have that many observations, so we'll come back and talk about how to handle sampling variability. But before I do that, there's one more thing, there's one more matter to be resolved, which is to talk about what are the constraints that this model imposes. So here I'm now going to give you another graph. So this is a graph representing the general situation where Z is the randomized variable, X is the treatment that people take, Y is the final outcome. This is not randomized, so there could be confounding between these two. And here I've allowed for the possibility that Z has a direct effect on Y, not through X. Okay, so these are my potential outcomes under this circumstance. So now I've got two treatments, Z and X, and so I end up with this set of 6 potential outcomes. Okay, and I can talk about the potential outcomes for X. This is what patients do when they're assigned to when they're asked to take the drug versus when they're asked to take the placebo. So we have patients who always take the drug no matter what. In this simple experiment, there were none of them because if you're assigned to Z equals 0, you had no way to get the drug. There could be people that are never takers. We did have some of them in the experiment. There can be people that are compliers. They're the ones that do what we wanted. And if everyone were a complier, obviously our analysis would be very simple. We just boil down to the previous randomized experiment. And then we have people that are defiers, or also known as 3-year-olds, who do exactly the opposite of what you ask them to do. Okay. For a general model, we would have also 16 types for Y. But we're going to make the assumption that we know somehow that Z has no direct effect on Y except through X. Okay? So in that circumstance, our Y potential outcomes go back to the ones we saw before: helped, hurt, always recover, and never recover. And our randomization assumption is just that Z is independent of X of Z and Y of X for each pair of values, X and Z. So these assumptions that there's no direct effect of Z on Y, and that Z is randomized, where if I'm precise about it, I mean this, are sufficient to justify the intersecting polytope analysis, that simple graphical analysis that I showed you a moment ago. Okay, so just to tie this back into the way we were looking at things before, here are my potential outcomes. I assign people to Z, then that then gives me, I then go over to this table, and that then tells me their X, their actual X value. So for example, this person is a complier. They were assigned to Z equals 0, so they have X equals 0. And then we then use those X values, we recursively feed those in to then find out what their Y potential outcomes are. What their actual Y outcomes are by reading off from the Y potential outcomes. It's by recursive substitution. Okay, and then this is our missing data that we have. Again, removing the entries that we don't see. But now, whereas previously Z was randomized, now here, because of dependence between X of Z and Y of X, that's the dependence that say, the compliers might be people that know that the drug is oh, sorry, the always takers might be people that know they really have to get the drug, and the never takers might be people who know that they're going to be hurt by it, so they're not taking it. So we don't have X randomly assigned anymore, but as we saw, we can still get useful bounds on the average causal effect for X on Y. So we can also think about this, if we wanted to, we could think about this as a two-way table. Here we've got our 16 types being the 4 combinations of the compliance types, never taker, always taker, complier, and defier, and the 4 response types, always recover, help, hurt, and never recover. Okay. You'll notice that there are 2 entries in it. There are 4 entries here that are 0 in this table, and that's the direct consequence of the fact that we are supposing that Z has no direct effect on Y except through X. If there were anybody in here, they would be somebody who had a different X value depending on what their Z value was. There would be somebody who had the same X value regardless of what their Z value was, but their Y value would somehow change even though their X value stayed the same. Okay, so that's ruled out. Nobody can be in here because of our no direct effect assumption. Okay, so let me just say a few words about previous work on bounds on the ACE. So Robbins and Mansky originally derived what were called the natural bounds on the average causal effect. And these are not sharp in the context of defiers. So if there are defiers, these won't be sharp. And there are observed data laws that are inconsistent with the assumption that there are no defiers. Volke and Pearl derived a closed form expression for the ACE bounds in the presence of defiers using computational algebra. Okay? And they came up with expressions that are maximum and minimum over 8 different algebraic expressions. And to some degree, it was one of these things where you ask the computer the answer to this question, and then it comes back, and you just you're happy with the answer, and but it's not. To some degree, it was less clear where the expressions were coming from than is perhaps the case in the derivation that I've just shown you. So Phil David re-derived these bounds without explicitly using potential outcomes, though in his proof he uses potential outcomes. So he had philosophical concerns about using potential outcomes, and I'll come back to that a little bit later. An advantage of the approach that I've taken here, the simple approach where we basically just thought about these as separate observational studies and then put together these 2 polytopes, is that it extends to Z with finitely many levels. So up until now, I've just thought about having Z with 2 levels, but if I had K levels for Z, so you could easily imagine a randomized experiment where people are, say, offered some financial incentive to comply with treatment, and you could imagine you could have many different arms where people are offered different amounts of incentive. So this gives, we actually end up with a reasonably simple expression for the upper and lower bounds on the average causal effect. This is basically just this is just an algebraic version of constructing these polytopes for each one of my K different Z arms, and then intersecting them, and then finding the maximum and minimum. Okay? And we're exploiting the structure in order to get it down to this relatively simple form where we've just got one type of expression up to I, J, and Z here, and another type of expression that's across 2 different Z arms. In order to get it to this form, we're exploiting the fact that these polytopes, as we saw from our analysis, will all be defined by planes that are parallel to one another, which means that we can cut down our calculation greatly. We're also using the fact that, and this is something else that drops out the analysis, that that bounds on the marginal probabilities are in fact variation independent. So these 2 marginal quantities are variation independent. So if we're trying to come up with bounds on the average causal effect, this is very useful because we can just come up with bounds on this, and then we can come up with bounds on that, and that gives us that allows us to come up with upper and lower bounds on the average causal effect by taking the maximum here minus the minimum here, and the minimum here minus the maximum here. Okay, so let me just say a couple of words about other examples where these designs may be used. So one that I'll come back to shortly, this is an actual study where Z was advice on the flu from a doctor. So a certain set of doctors were randomized to advise their patients to get, or encourage their patients to get flu shots. And then X is whether or not you actually get a flu shot, and then Y is subsequent hospitalization with pneumonia. Randomized trials with non-compliance we already talked about. Educational interventions. So if Z is assignment to extra tutoring, and then X is whether or not the student actually attends tutoring, you face this problem that often you make extra tutoring available, but the people that show up for the tutoring are not necessarily the people that really need it. And then Y is some final test score. There are also studies that are being done, as I said, of the Smith and Jones variety, where you have two different drugs, and you would like to find out whether or not they are, whether you'd like to do a comparison study of these two drugs. And one way to do that is if you have doctors who have different opinions about which patient should be assigned to which drug, and you're in a sort of setting where patients come in and are randomly assigned to a doctor, as is the case in sort of university clinics, for example, then you can use the fact that people are being randomly assigned to a doctor to then and the fact that doctors have different prescribing preferences to then look at the difference between different drugs. Okay, so there's one more issue that I haven't dealt with yet, which is that the two polytopes might not intersect. Okay, so in the example I showed you, they did intersect, but it's perfectly possible to get data from two different arms where they don't intersect. Okay? And that leads to testable constraints on the joint distribution. So this is the same fact that we looked at earlier, that this entry has to be 0. Okay? So for example, if this column sum plus this column sum add up to more than 1, then we run into a contradiction. We can infer that there must have been a non-zero quantity in here, because we know that all of these 16 quantities have to sum up to 1. So if I'm adding up 4 of them here and 4 of them here, that also has to sum up to less than 1. So if when I add up this plus this, I get more than 1, I've got a contradiction. Okay? So this is the basic picture here. But now if I look at the counterfactual distributions that I have here, I cannot get all possible observed laws. There are pairs of distributions over pairs of observational studies that I could have that could not have that are not compatible with our assumption that Z has no direct effect on Y except through X. Okay? And when Z is binary, the set of the observable distributions are defined by these 4 inequalities, which correspond to those 4 0 entries in the table that I showed you just a moment ago. And so that gives us a subset of the observable distributions. So these IV inequalities were derived by Pearl originally and extended a little bit by Bonnet, and they provide a test of the binary IV model. And interestingly, initially when you see these, you may wonder how can they be interpreted. It turns out they can be interpreted as bounding away from 0 the average direct effect of Z on Y holding X fixed at X. So going back to this picture here, it turns out, I don't have time to tell you about this, but it turns out that we can sometimes get bounds on the direct effect of Z on Y holding X fixed. And so if we can infer that this effect, if we can bound it away from 0, then that means we obviously can rule out the possibility that there's no edge from Z to Y. So that provides the test of the IV model. Okay. So yes, it's not immediately obvious how to visualize this set. Right? This is basically a subset. Our original set of distributions is a product of 2 3-dimensional simplices, and now we've got these restrictions on them. But one thing that we can do is we can take the left-hand side of all of these and create some new coordinates. So call this the sum of these two things U1, the sum of these two things U2, the sum of these U3, and the sum of these U4. We know that the sum of all these things add up to 2, so consequently we can project from the product of these 2 3-dimensional simplices down into an ordinary 3-dimensional simplex, but where things sum up to 2. And if we do that, we then get so the projection of our set of possible distributions turns into this little octahedron in here. Okay, so this is the image of our 6-dimensional space going down into a 3-dimensional space, just to help us visualize it. And that gives us as an immediate corollary, because each one of these little bits corresponds to, each one of the corners that we've cut off here corresponds to one inequality being violated. We get as a corollary that at most one inequality is ever violated. Okay, so I haven't yet explained to you why it was important to work out to describe the observable model, but I will now briefly, in describing to you some of the issues that arise for doing statistics with these models, we will now make use of this. Okay, so as I said earlier, I said I just plugged in the empirical distribution as if it were the population distribution, and that could be thought of, in this context, could be thought of as just computing maximum likelihood estimates. But still, we might want to take into account sampling variability. And so one way that one way that it was proposed to do this, proposed by Pearl, was just to put a Dirichlet prior on the set of all of those types. Okay, so our set of types lives in this 15-dimensional simplex, so that we have these 16 types. So the idea was, let's just put down a Dirichlet prior and then just crank the handle of Bayesian inference. Use MCMC to sample from the posterior distribution. And now I'm going to show you, I'm now going to critique that. Okay, so here, this is going back to the lipid data. So in that data, we only had compliers and never takers were the only two compliance types, because everyone in the control arm got placebo. And we've got our, so we have 8 types: complier and always recover, complier and helped, complier and hurt, complier and never recover, and then the same for never taker. So here I simulate from the prior. So I just put in a uniform prior, Dirichlet 1, 1, 1, 1, 1, 8 ones there. And then now here, these are the marginal posterior distributions. So these are the marginal prior distributions. These are the marginal posterior distributions, okay, obtained using MCMC. Okay. And here, here's the prior distribution over the average causal effect. And here's the posterior, the average causal effect. These dots are the bounds that we obtained before, that we got by intersecting those two polytopes and reading them off. And so this, in a certain sense, you can see this interval as being the maximum likelihood estimate, and here we've got a posterior, and you can see that they're roughly agreeing with one another. However, there's a problem. The problem is that this is one of these Bayesian models that your parents warned you about. Okay? Which is to say that if we make a small perturbation to the prior, this is an under-identified model, and if we make a small perturbation to the prior, things will change. Okay, so here, what I've done is I've gone from Dirichlet 1, 1, 1, 1, 1, 1, 1 to Dirichlet, I've moved 0.2 of a person from one category to the other. So those of you who are familiar with Bayesian inference, these things sort of have can be interpreted as, roughly can be interpreted as sort of equivalent sample size. So this sort of has the information content as if I roughly, have to wave our hands a little bit, had 8 observations, and I've moved here 0.2 of a person from one category to another. Okay? A very small perturbation of a prior. The data that we had, remember, the data we had, way back wherever it was, our smallest count was 12. So it's not that we had counts down in the sort of single digits. Okay. So now I make this small change, and you can see here, if you just look at this, you can see that I've got this change in these two. Okay? So, and this matters, because this is never taker and help, this is never taker and never recover. Okay? So this is going to change the average causal effect. So here, this is what happens to prior. As you can see, the dotted line is the perturbed prior, and the solid line here is the original prior and posterior. So dotted is the perturbed prior and posterior, and solid is the original prior and posterior. Okay, so we've got, you can see we made this tiny change to our prior, and we got this, we wiggled our posterior. Okay, here I've got the median, so you can see the median's also moved. So you might not get very excited about this, but I make the point partly because sometimes, in fact, what provoked me when I first saw this was Ruben gave a talk where he did a causal analysis, and he said, and somebody said, well, this is great, but your parameter is not identified. And he said, I'm a Bayesian, I don't care about identification. Okay? And there is a sense in which that's true. If you happen to know your own inner beliefs perfectly, you know exactly which prior distribution you're doing, and you want to compute your posterior for your own information, that's great. But if I think my prior distribution might be slightly different from, say, Jeff's prior distribution, there's not really particularly any reason, as we can see, why I should pay attention to Jeff's posterior. If were my prior to be slightly different from Jeff's, I would get different conclusions. More to the point, this model is under-identified, and common intuitions that people have about prior sensitivity don't apply. So when I came up with this phenomenon, I asked various Bayesians, and they said, oh, well, this is just because your prior wasn't diffuse enough. The likelihood's fighting with the prior. Just make the prior a bit more diffuse. Go with a unit information prior. Make it even more diffuse. Get rid of the Dirichlet 1, 1. You can see here that prior, it's not going the whole range from -1 to 1. You should just, be more laid back, have a more diffuse prior, and all of these problems will go away. Okay, so I put in a 1/8, 1/8, 1/8, 1/8 prior, and then we have a slight perturbation. I'm moving 1/16 from one category to another. But we might ask the question, whose unit of whose information is this? And as we can see, it actually makes the problem worse. Okay? So here we end up with this sort of Dr. Seuss posterior here. So the solid red line here is the posterior when we started off with Dirichlet 1/8, 1/8, 1/8, 1/8, and then the dotted is what you get when I make this tiny perturbation. Okay? So that we've actually did prior sensitivity by making, sure enough, our prior here is more diffuse, okay? But this slight perturbation is now having even more impact. Okay? We've got a strongly bimodal posterior. Okay, so the question is how to get around this problem. So how to formulate the priors transparently. And I also am belaboring this a little bit because, for example, if you have attended some other talks on causal inference, sometimes it's sort of described as if once we've worked out whether or not something is identified and once we've drawn our graph, then everything else is just details. It's just a question of decorating the graph with numbers or probabilities. Okay? And as you can see here, there are actually some subtleties about doing the statistics correctly for these models because these parameters are not identified. Okay, so here's how we get around this problem. We have to reparameterize. Okay? So our original parameters, the problem was that these are a mixture of things, some of which are identified and some of which are not identified. So the way to get around this is to reparameterize into a parameter that's identified and a parameter that does not show up in the likelihood. Okay? So we're going to reparameterize into these two things. Theta, that's just an ordinary identified parameter, and aleph, something that's not, that's completely, that does not show up in the likelihood. We could have I've made the prior here between these two independent. If we wished to, we could have a prior that allowed these to be dependent. It wouldn't change the analysis significantly. Okay, so how do we do this? Well, the way that we do it is we're going to do the obvious thing, which is we're going to just use the observed distribution to parameterize our model. We know what the distribution of the observables is. We know it's defined by these four inequalities that we saw earlier. So what we're going to do is put a Dirichlet distribution on the unrestricted distribution over the observables. This is very different from putting a Dirichlet distribution over the types because this is identified. Okay? This is identified. Once we're up to 12 observations, we're not going to have to worry about small perturbations. Okay? It should be noted that the problem that I described, this problem of prior sensitivity, it wouldn't matter how much data I had. We will continue to have that problem of prior sensitivity because there's no way that we can ever learn about the ratio of those two particular types. So if I had had thousands in my data set, it would not have changed this particular sensitivity. Another way of saying it is there are aspects of the prior that you're stuck with forever, basically. It doesn't matter how much data you Okay, so then in order to do inference here, I'm just going to put down Dirichlet distribution on 2 Dirichlet's on this, on the observed data law, one for z equals 0, one for z equals 1. And then I can then compute the posterior via usual conjugate analysis. And then all I do is just truncate, throw out those distributions that violate these inequalities that define the model. And in that way, we can perform inference using straight Monte Carlo. So I just simulate from this Dirichlet distribution and eliminate distributions that violate these inequalities. Okay? So that's all that this says. It says, put down Dirichlet, compute the posterior, simulate from this posterior, and then throw out things that violate the inequalities. Okay, so going back to our lipid data, I'll just skim through this quickly. We had 2 structural zeros, so there are actually only 6 probabilities that we need to put our prior over. We have 1 for the x equals, we have a Dirichlet 1, 1 for this distribution, and Dirichlet 1, 1, 1 for this distribution. We then truncate and renormalize using IV inequalities. And so this is what we finally get. So now, instead of actually putting a prior over the parameter that was not identified, this analysis is simple enough that I can just show you what the posterior would be for every possible value of this unidentified parameter. Okay, so that rather than my forcing my beliefs about this thing that we can never learn from the data onto you, I can simply show you what your posterior would be for any value of this unidentified parameter. Okay, so this is the equivalent of Aleph. This is a parameter that tells me the probability of a good outcome for never takers if they were to get the drug, and this is completely unidentified. Okay, just mention another way that you might want to extend this. Statisticians want to model everything as a function of baseline covariates, so including possibly continuous baseline covariates. So we can again use this description as a model in terms of these inequalities. You can just think of this as being like a slightly more complicated version of the way that logistic regression works. So basically, I just need to have a multivariate link function, or diffeomorphism, that takes me from R to the 6, because I have a 6-dimensional space, into the subset of these 2 3-dimensional simplices given by the inequalities defining the IV model. Okay, so I just want to have, whereas logistic regression, you can choose any value on the real line and plug it into your logit function, you get back a probability. Here, I'm now going to plug in these 6 numbers, and I'm going to get a point that is in the set of probability distributions that are defining the model. And then we can incorporate covariates just as if this was a multivariate generalized linear model. Okay? So parameters, in order to get this to work, we have to have parameters that are a little bit more complicated. This basically is incorporating the IV inequalities in a sort of log barrier style approach. And then this is just a little illustration of this. This was the flu vaccine data analysis done by, that was looked at by Hirano et al. So here now, Z is whether or not the patient's physician was sent a card, X is whether or not the patient did in fact get a flu shot, and then Y is their outcome. So so all of these patients, the doctor encouraged them to get a flu shot. These doctors were not prompted to encourage their patients to get a flu shot. They didn't discourage them, but they just were not encouraging it. And as you can see, there are still some people who got flu shots anyway, and there's still some people who didn't get flu shots anyway. So in the analysis, there was a pre-existing condition, chronic obstructive pulmonary disease, and age were identified as important covariates because the outcome here is hospitalization for pneumonia. So we put diffuse Gaussian priors over these 6 generalized linear models that we set up. So we have all of these parameters, and then we Bayesian inference via standard Metropolis Hastings. And we then get to this plot where now here we're plotting upper and lower bounds on our causal estimand with posterior intervals for those upper and lower bounds. And I won't go into details here, but the basic point is this shows that our upper bound, this is a very sophisticated way of saying we can't tell anything because basically the upper bound and the lower bound always contain 0. Okay, I'll make a few comments about relating counterfactuals to other frameworks. So the first, how many of you have heard of Pearl's do notation? Great. Okay, so Pearl's do notation, written in this way, talks about distribution of y when we intervene to set x equal to x. This just corresponds to this quantity that I've been writing in this way. And Pearl's do notation, of course, everything, it's always, there was a very similar notation called G notation introduced by Robbins in 1986. The counterfactual notation, however, so although we can always convert do statements into counterfactual statements, there are counterfactual statements that don't have any direct analog to do. So, for example, we could talk about the distribution of outcomes that would arise among those who took treatment had counter to fact they not received treatment. Okay, so if we think about something like the educational study that I told you where we make extra tutoring available, but then all the people that actually sign up for the extra tutoring are the people that didn't really need it anyway. So in that case, the effect of treatment on the treated might actually be very small. So the effect of treatment on the people who took treatment might be very small because they would have had, they are all the studious students who would have had good outcomes anyway. So if treatment's randomized, then this will just be equal to the outcome, the average outcome if everyone were to receive placebo. But if people are selecting treatment, if the people that are selecting treatment are not representative of the population as a whole, then this quantity will be different from this. The key point here is that this cannot be expressed directly in terms of the do notation, okay? Because we're looking at people who actually chose to take treatment, and then we're looking at the distribution of outcomes among that subset of people, the distribution of outcomes that would arise if they were to get control. And we can't do that with do, because do notation, if we're setting x to x, then we're not allowed to also talk about what x would have been had we not set x to x. We need to have counterfactuals to do that. Okay, how many of you have heard of non-parametric structural equation models or structural equation models? Okay, so I'll mention this briefly. Pearl, so these are also called structural causal models by Pearl. This is really just another way of writing potential outcomes. So the idea is that if I have my graph like this, then I have an equation for x as a function of an error term. I have an equation for m as a function of x together with an error term for m. And then I have an equation for y as a function of x and m and an error term for y. Okay? If you think about it for a little bit, you can see that I can actually go backwards and forwards. I can just think of this error term as being the potential outcomes, and then you can think about the function as just selecting the particular potential outcome. So these two languages they're just two different ways of writing the same thing, and it's even clearer if instead of writing it like this, we write with the random versions in here. If we write each of these structural equations in terms of potential outcomes, then the translation between these two different notations becomes absolutely clear. Okay, and then the observed variables, if I write it like this, I then get the observed variables back by recursive substitution, which then gets me back to the form that I have over here. Writing it in terms of counterfactuals makes clear that these equations are representing invariant relationships. Okay? So intervening to set x and m to 0, the value for y would be 0, 0, epsilon y. Y of 0, 0. So there's an alternative way, the way that people who work with structural equations, and this is also the way that Pearl usually describes it, think about this, is they think about crossing out equations. So they think about the intervention to set x and m to 0 would correspond to crossing out this equation to replace it with an equation that says m is 0, and crossing this out to have an equation that has x equals 0. That's a perfectly well-defined way to proceed, but there is a notational ambiguity that arises, because then y in the system after, the y arising in the system after I change two of the equations is not the same as the y in the system before I change those equations. In the potential outcome notation, that's all taken care of, because I'm indexing things by the interventions I'm making. There are some, although these are two syntactically equivalent objects, there are actually some differences in terms of the way that people think about them. So one difference is that when people put down a set of structural equations, as you can see from here, it's implicit that I can intervene on every variable. Okay? That's the way people think about these systems. So, right, if Pearl's structural causal model, it's just ab initio. When it comes out of the box, you can intervene on any variable you want to in it. Okay? I just tell me what you want to intervene on, I'm going to cross out those particular equations. Okay? And if I have a set of, if I'm thinking about an electronic circuit, then that may be very reasonable. But a lot of examples where people build causal models, the idea that you can intervene on every possible variable and know what you're talking about can often start to seem somewhat ridiculous. So for example, suppose that X here is, supposing this is some telephone survey, X is some prompt. We read you some bit of text that's supposed to get you worked up or about some particular topic. And then M is the next question you're asked on the telephone survey, and then Y is the second question you're asked on the telephone survey after this prompt. Okay? So in this case, X is some prompt that we're manipulating, M is your answer to the first question, and Y is your answer to the second question. Of course, I could write down a model like this, but now if you start talking to me about what it means to intervene on M, this means you're now talking about the possible world where somehow you intervene in my brain and make me give a particular answer to a particular question. Okay? It turns out that, actually, I guess maybe many people know about this, there are ways of doing this by directing electromagnetic fields at parts of people's brains in order to get them to give particular answers. But still, at the moment, getting somebody to give a very specific answer to a question, I think this is still in the realm of science fiction, and so talking about M of X here people would think this is not necessarily well defined. Okay? A second point I'll come back to is that typically Pearl doesn't just use this as a syntactic representation, he also assumes that all of the error terms are independent. And there are for very subtle reasons that leads to, that assumption is non-empirically testable via randomized experiments. And I think that's a thing that has led to a lot of people having worries about the non-parametric structural equation model approach. Okay, so far here's the summary. Potential outcome framework allows causation to be reduced to missing data, right? Which I often describe as causation is something that everyone for thousands of years has been excited about. Missing data is something that some statisticians get excited about, but fewer people get excited about. But I think generally the fact we've taken something exciting and turned it into something that fewer people are excited about shows that we've made conceptual progress. I will contrast this with Pearl in his talk, in his tutorial, says that he doesn't say that this can't be done, but he says that he doesn't like this to be done because he would prefer to think of this as a revolutionary paradigm shift where we went from missing data to thinking about causation. And I can come back to that point in the discussion. Ultimately, we are just, we don't disagree on any of the math results. It's just a question about exactly how to get, how the infomercials for those results are put together, where there are differences, or how basically when the results are being described to people, where the motivation for a particular framework is cast. Okay, so we also saw that under randomization, the average causal effects identified. We saw that the instrumental variable model provides a way to bound causal effects under imperfect randomization. We saw that since potential outcome models are only partially identified, care is needed when we're doing Bayesian analysis. Then I also want to make this point that sometimes statements are made saying that statistics has turned its back on causation and that nobody ever does any causal analysis in statistics. This is, certainly there could be more statisticians doing causal inference than there are, but there are still thousands and thousands of people doing causal inference in statistics, and there's a very large literature using potential outcomes. As I'll argue in the next part of the course, I think that, of this talk, I think that graphs have much to contribute and can make potential outcome analyses clearer, but we should not pretend that there is no causal analysis being done currently in statistics. And indeed, there are many more applications of currently, many more applications of potential outcome framework to real problems done by people in biostatistics, epidemiology, and econometrics than there are of the graphical approach to causality. So the next part of my talk, in some sense, is to provide a link from people that use graphs to potential outcomes. So this is going to be about combining graphs and potential outcomes. Okay, and so I'm going to give you a very simple node splitting operation on a graph. This is going to be a graphical operation that allows me to link graphs to counterfactors. I'm going to show you simple examples that are even simpler than the simple examples we looked at earlier. I'll then tell you about a general procedure. I'll talk about factorization and modularity, which is sort of the minimal assumptions needed to get this show on the road. And then I'll talk about adjustment for confounding. Okay, so you may remember I showed you these two graphs before. We said this one on the left was no confounding, this one on the right was confounding. Because there's a convention that says when I write down a graph, if I have if there's a hidden variable, then I'm obligated to put it on the graph if I'm going to interpret the graph causally. Okay. And this graph, just as the potential outcome framework goes back to the 1920s, the graphical framework also goes back to work by Sewell Wright. Okay. And a little bit of, if I have a directed edge, then x is a parent of y and y is a child of x. Right? So although we've got, this is sort of mind-blowingly obvious, but although the edges are directed, simply the fact that my joint distribution factors according to a graph doesn't say anything, because obviously any distribution can factor according to this graph and can factor according to this graph. Okay, the graphical approach to confounding, the graphical approach to causality says that if I have this graph and I have this factorization, what makes the, under graphical framework, in the absence of confounding, the causal model, if I'm now interpreting this as causal, the extra piece of information is that I'm now saying when I write this, that if I were to intervene on x, then the distribution of y, when I intervene on x, is equal to the conditional distribution for y given x. Okay? So we're saying that this term is invariant under interventions on x. And so that the average causal effect will be identified under this model. The question is, how does this relate to the non-graphical approach? Okay, so there's an irony here. So let me get a quick show of hands. How many of you have heard of D-separation? Okay, so many of you are familiar with the fact that if I give you a graph, you can read off conditional independence. Okay? So here we have this setup. So I have a graph. And as you saw earlier, under the potential outcome framework, so this graph is supposed to mean a randomized study or no confounding. And we saw that we associated that with these two independencies. And we have a graph here. Likewise, this was supposed to be associated with these not holding. And graphs are presented quite justifiably as being this wonderful engine for reading off conditional independence. So it would seem quite natural under these circumstances to think, okay, great. So you know, this is a causal graph, and no confounding is this independence. So now all I need to do is read this independence off this graph. Okay? But there's an elephant in the room here, which is it doesn't matter how long you stare at the variables on this graph, you're never going to see y of x0 on the graph. It just is not there as a variable. They don't appear on the graph. And this, for example, Rubin has used this as a criticism. He said, how could these graphs possibly have anything to do with causality? We know that causality, at least in statistics, is formulated in terms of potential outcomes. The graphs don't have potential outcomes, so obviously they're not doing anything to do with causality. So we're going to fix that. We're going to fix it via a very simple operation. We're going to split this x node. We're going to split it into a random part, which will be think of that as the natural value of x, and then a fixed part, which in this case I'm now fixing to set equal to 0. And then everything that's downstream of that fixed value is now going to be labeled with y of x equals 0. And now, although I've made this semicircular just to remind us how we came upon this graph, to remind us that if I'm looking at the right-hand side here, I can remember that I got this out of this graph on the left-hand side. But I can now, even if you don't remember the definition of d-separation, you can remember it has something to do with there having to be a path, and there's no path that goes from x to y of x equals 0. Okay? So we can read off the independence directly that x is independent of y of x equals 0. Okay? I also have to tell you, I'm now going to use this graph over here to represent a distribution over x and y of x equals 0. Okay? So in order to do that, I need to tell you which distribution. Well, the first thing I'm going to tell you is that the distribution factors in exactly the way that a Bayes net usually factors, okay? Just ignoring these fixed parents. Okay? So here, if I just ignore the fixed parents and I just have two nodes that have no parents, so my joint distribution factors into these two independent pieces. Okay? So the factorization I'm going to associate with the new graph is going to be the usual Bayes net factorization, just ignoring the fixed nodes. Then I also have to tell you, where am I supposed to get this new marginal distribution from? And I'm going to get that in the obvious way, a way that will seem intuitive if you're used to the truncation formula. I'm just going to take my original factorization like this, and I'm going to plug in x equals 0, and I'm going to use that to get the marginal distribution of y of x equals 0. Okay? So this term links the terms in the new factorization back to the original factorization of the observed distribution. Okay, so everyone clear on what we did? We had a graph, we turned it into this new graph, and I came up with a new factorization over my new variables by just using this piece with x equals 0 for my new distribution over this. Okay, so notice here that x tilde is not set to x equals 0. I could ask what's the probability that x is equal to 1 and y of x equals 0 is equal to 1 as well. Okay, so this x tilde is a different variable from the one here that's now bound to take the value 0. I could also split and set x to 1. Okay, if I do that, I get this graph. Okay, and then I can read off this other independence, x independent of y of x equals 1. And I could associate a new factorization where here now I'm just plugging in x equals 1 in here, okay, to get my other term. Okay, you might think, well, why isn't this a bit heavy-handed? Why am I having to do this for both these two values separately? And the reason is that I'm not going to draw a graph that has y of x0 and y of x1 on it at the same time. And the reason is the following, that I'm going to want my graphs to represent distributions that, under my assumptions, are identified if I observed everything in the original graph. So if I observed all the variables in my original DAG, then the counterfactual distributions that I'm representing by node splitting are also going to be identified. Okay? Had I constructed, so as we saw under no confounding, these are identified from the joint distribution here. So the node splitting operation preserves identification. In contrast, if I had tried to be more ambitious, and I had tried to construct a graph that had all of these things on it, x, y of x0 and y of x1, or maybe I could even have gone for x, y of x0, y of x1, and y, then I would be putting down, having a graph that now represented things that could not, in principle, be identified. Right? We went through and saw that the analysis at the start of the talk, we saw even under randomization, I cannot identify the joint distribution over these two guys. I don't know the distribution over helped, hurt, always recover, and never recover. So consequently, in my scheme, I'm never going to put these on the same swig. So I'm going to be able to read off this independence, I'm going to read off this independence, but I'm not going to be able to read off this independence. Okay? Which I might be quite willing to assume this independence if x really had been randomized. I might be willing to assume this independence. But this is a statement about a joint distribution that is not identified. Okay? And had I tried to construct a single graph containing both y of x0 and y of x1 and x, then as soon as, if I was formulating things via a path property, then as soon as I had no path from x to y of x0 and no path from x to y of x1, I would be stuck with having this independence here. Okay? So in order to get around this, I'm never going to put both of these variables on the same graph. Which is why I belabored the point about first splitting on x equals 0 and then splitting on x equals 1. Those form two separate graphs that represent two different margins. And the single word world here the single world here refers to the fact that I'm not going to put both of these together on one graph. Of course, it gets tedious to have to draw a different graph for every value of x, especially if x takes infinitely many values. So I can represent this as a template like this. But if I do this, I have to realize what this thing is. This is now a graph-valued function. It's not a graph. Right? So you come along to me and you plug in your favorite value of x, stick that in there, and that then gives me a graph that represents x and the potential outcome for whatever your favorite, whatever value of x you happen to stick in. Okay, so each instantiation gives me, represents a different margin. Okay, so let me give you a little bit of intuition behind node splitting. This is also going to be a little bit of a humorous interlude. So you might say, okay, so this graph here allows me to see both. I'm going to be able to see that certain people have x equals 1 and have y of x equals 0. Okay? I mean, I'm going to be able to see both. For example, the effect of treatment on the treated, I have to be able to, I'm saying that distribution over x and y of x equals 0 is identified. So that means there are certain people that I'm going to be able to see that naturally would choose the treatment, and then I'm going to be able to see what would happen to them if they didn't get the treatment. So you might think, how could I possibly have an experiment where I could do both of those? Where I both see that somebody would choose to go to the extra tutoring, but at the same time also find out what happens to them when they don't have this tutoring. So this is the thought experiment that my MD co-author Jamie Robbins came up with. And I described this to you because it will help to give you a sort of mental picture for what the node splitting is doing. So he said, if we want to identify who are the people that would take treatment and find out what happens to them when they don't get treatment, what we do is we just carefully we tap into the NSA data feed from their house, and we just watch them until the moment where they swallowed the drug, or they got the vaccine. We just, at the moment when they do that, we just swoop in, and then because we're a doctor, we administer a safe emetic that then leads to them regurgitating the pill, so that we both get to, before the drug has entered their bloodstream. So we both get to see that they naturally would choose to take the drug, and we get to see what happens to them when the drug does not enter their bloodstream. And that is that thought experiment. Not that you would ever actually do this, but that thought experiment is corresponding to the slicing of the node in half. I should say that there are less graphic contexts where people do something like this, where, for example, people will request to be part of some, for example, to get extra tutoring, but there is not enough extra tutoring available, so people are randomly selected. So certain people who express the desire to go to the extra tutoring are not actually able to get it. Okay. So let's do a harder inferential problem. So that was very easy, just had 2 nodes. Now I'm going to show you, this is a sort of little calculus for reasoning about counterfactuals. I'm now going to show you a slightly harder example. So let's consider this graph, and let's ask the question, does this graph imply this particular conditional independence? Okay, so now we split on A and we split on B. And everything, so we'd first do our splits, and then everything downstream of the fixed node A gets labeled with A, and everything downstream of the fixed node B gets labeled with B. And we can then read off from this graph, we can then see, well, is B of A d-separated from Y of AB conditional on this and this? Okay. And if you remember d-separation, you'll see, yes, there are 2 paths from here to here. There's this path and there's this path. Z of A is a non-collider on both paths, and it is so both paths are blocked, conditional on Z of A. I've also conditioned on A for reasons that will be clear, capital A, for reasons that will be clear in a moment, but the d-separation would hold even if I had not conditioned on capital A. So applying d-separation to the swig on the right, we can see there's no deconnecting path from Y of AB to B of A given Z of A. So this was a more complicated example. Now let me give you the general procedure. And the general procedure basically is no more complicated. I mean, it's basically just an elaboration of what you've seen. So if I want to intervene on a bunch of variables, I just split all of those variables to create two new nodes, one part of which is random and inherits all of the edges in, and one part of which is fixed and inherits all the edges pointing out. And I then just label everything downstream. So this is slightly busy, but all it's saying is that if I have after I've done all my splits, I then let everything downstream of this fixed node A be labeled with little a. This is to indicate this guy doesn't get labeled with little a, and this is to show that B, for example, is also split, and anything downstream that's only downstream of B is not getting labeled with A. So that's my procedure. And then that gives me my template, and then I then stick in particular values for the variables A and G of A. And then the new graph that now contains a set of variables and represents a joint distribution over those random variables. Okay. So the factorization and modularity assumptions just are elaborations of the assumption that we saw earlier. So first we just assume that the random variables in the new graph factorize according to the graph just as if it was an ordinary graph ignoring fixed nodes. And then modularity just links for each random node, links it back to the original factorization by saying conditional density associated with my new variable is just the conditional density associated with the original random variable, substituting in values for any variable that is that has been fixed. Okay. And so the consequence of this is, as I said, if we have observed the joint distribution over all the variables in the graph, then after I do all of these splits, the new distribution is identified. Okay, so we can now apply d-separation to this graph, and so we're going to apply Pearl's d-separation criteria. That's going to be our central workhorse for using these graphs. Will be that we can read off conditional independencies by applying Pearl's d-separation. The only thing we have to do is basically to just add the qualification that we ignore fixed nodes, okay, so that we have exactly the same definition of d-separation, deconnection, but in order for a path to be deconnecting, it must not contain any fixed nodes. Okay, so then basically, if I give you under factorization and modularity, I can then read d-separation off my new graph, and then that will correspond to conditional independence, holding in the distribution over those potential outcomes. Okay, so here are two little examples. So here, if I have this is the mediation graph. I intervene on Z. I get X of Z and Y of Z. Right? So I first split on Z and then label everything downstream. Factorization says that the joint over these three variables takes this form, Z, X of Z tilde, because it has no random parents, and then Y of Z tilde, given X of Z tilde. And then modularity says if you want to know where these came from, I just go back to my original factorization and obtain these new pieces from the original factorization. D-separation says that Z is d-separated from each of these because there's no path from Z to either of these nodes. Okay. Here now I've intervened on both Z and X. I then get this factorization here, which just says everything is, all the variables are now marginally independent in the counterfactor distribution. Modularity is basically the same, similar to what we had before, except that now both X and Z have been fixed. So now this is X tilde and this is Z tilde. And d-separation gives me, for example, that X of Z tilde is independent of Y of X tilde Z tilde. And that's because although we have what looks like a path here, our rule for deconnection says that this has to be, that we can never have fixed nodes on any deconnecting path. So although it looks like we have a path here, it is, this is blocked. Okay. So another way of saying this is you could just check d-separation by throwing out all the fixed nodes to start with, but there's a reason why the fixed nodes are useful. There are two reasons why the fixed nodes are useful that I'll mention briefly. So here's the no direct effect graph. Now I have no edge from Z to Y. And so when I intervene on Z, I now get this, this factorization, modularity, the following conditions. And because y is independent of z given x, I also get that, that y equals y given x equals x is equal to this guy. D-separation, so this is capturing the fact that we have no direct effect of z on y when we're controlling for x. D-separation gives me that z is independent of both of these. The reason why it's useful to keep the fixed nodes around is that, think about, we looked at this example and we looked at this example. After I split on z, I get this graph. If I'm doing this, after I split on z here, I get this graph. And although the factorizations that I have are the same, the modularity condition is different here than it is here. The modularity condition here says that y of z given x of z is equal to, down here is equal to just y given x, but up here is equal to y given x and z tilde, okay, because of this edge here. So the basic point is, one reason for keeping fixed nodes around is that if I want to be able to look at these graphs here and work out where did they come from, what was the original graph, I need to keep the fixed nodes around. If I'm keeping these graphs here anyway, then I don't necessarily need to keep the fixed nodes around. But if I want to be able to look just at this and recover where I started from, which sometimes is useful, then I need to keep the fixed nodes around. Because otherwise, if I got rid of the fixed nodes, if I get rid of this and get rid of this, then I end up with the same graph on the right-hand side, and I can't tell which one this came from. Okay, so let's talk a little bit about adjustment for confounding. So how many of you have heard of the backdoor formula? Okay, so backdoor formula or adjustment. It's just a formula that says, in a circumstance like this, we have a study where x will not be independent of y of x, but it will be independent of y of x given L. So this is, for example, this is a situation where the doctor was flipping a coin to assign treatment, but they assigned which coin the doctor flipped to depend on some observed covariate L. So the doctor used a different coin for males versus females, for example. Okay, so we can see here, we can read off from this graph immediately just d-separation again, x is independent of y of x, conditional on L. Okay. And we'll see in a second this leads to this simple formula that just says if I want to know the distribution of the intervention distribution y given do x, then I obtain it from this formula by just taking y given L and x equal x tilde and multiplying it by distribution of L equals L. This is, in epidemiology, this is called standardization. In the graph literature, it's often called the backdoor formula. Okay. So here are two different ways to derive this for this graph. One way is that I just start off with this, and by rules of probability, I can write this in this way, just by the chain rule of probability. And then by modularity, I can then write it in this form. Okay, so modularity just gets me from here to here. Okay. An alternative way is that you can use this independence here to add in x equals x tilde here, because y of x tilde is independent of x given L. So I can add in x equals x tilde here. And then consistency, that's the tautology that we had way back at the beginning when we talked about potential outcomes, means that among people who actually get x equals x tilde, then y of x tilde is equal to y. And so then I get to the same formula here. So the typical way that this criterion is checked is to construct a mutilated graph where all edges are just cut out of x. And then you test for d-separation in the graph that we get in this way. So this is the approach that Pearl and others have proposed for checking whether a particular set of variables is sufficient to control confounding. That approach is very nice if we're considering a circumstance where we're thinking about the null, where, say, x has no effect on y. It makes clear, well, if x has no effect on y, well, if I just looked at the marginal association between x and y, I would have a non-zero association. So I couldn't just use the distribution over x and y without taking account of L. But if I condition on L, then I can see, yes, x and y will be independent. But this graph doesn't really explain why L is sufficient to control for confounding under the alternative, so when X does have an effect on Y. But I should say, I mean, this is just about pedagogy, really, because Pearl's criterion is equivalent to ours, and hence Pearl's criterion is valid under both the null and the alternative. So here are more examples. So if supposing I had an extra confounder between X and L, well, if you're familiar with this way of check it, this won't seem surprising to you, but you can just see, yes, if I have a confounder here, X and Y of X are independent conditional on L. If I had a confounder over here, I would get the same thing. If I had both confounders and they were independent, then I would be stuck, because X and Y of X would not be independent conditional on L. Here's the instrumental variable model that we saw earlier. So just tying back to that earlier part of the tutorial. If I intervene on Z and I intervene on X, then I get this graph over here. And we can read off from this graph these independencies. And these independencies were sufficient, as I noted earlier, were sufficient to derive the ACE bounds that we looked at. Okay, I've made this point already that we're not allowing these joint independence relations. The reason that we're not doing that is that, well, I can maybe I can explain in the question and answer that allowing this independence looks pretty reasonable if I actually randomize X. Why shouldn't I assume that X is independent of both these potential outcomes? But in the case where we have more variables, then once we start allowing these cross-world independencies, we get additional identification results, and those are additional identification results that couldn't be checked by any experiment on the observed variables. Okay, so let's go back to this inferential problem. So here we have this graph. Here we did this intervention. The reason this is interesting is that in a previous edition of Pearl's book, he also has a way of connecting graphs and counterfactuals. And he claimed that the graph over here did not imply this particular independence. And in fact, we can see in 2 lines that this does hold. We have to do a couple of additional steps of inference, but we can easily see from this independence here that we read off the graph, Y of A, B is independent of B of A, conditional on Z of A and A. That was what we read off. And if we condition on A equals little a, then by consistency, Z of A is equal to Z, and B of A is equal to B. So we can see in 2 lines, we can get from here to here, and then back to here. So this is very interesting that Pearl, in this analysis, thought that this independence was not implied by this graph. I should add, Pearl typically interprets DAGs, when he interprets them counterfactually, he makes more independence assumptions. So his model is a submodel of ours, but so consequently, anything we can read off from the SWIG will also hold in Pearl's model. But Pearl's model in general will have additional independencies. So I should add here, there's a story about a famous epidemiologist that he never made any mistake except for once when he thought he had to correct himself. And that basically this also applies to the story about Pearl, because Pearl, in putting this in the 2nd edition of his book, he thought he was correcting a claim that he thought was erroneous in the 1st edition, but in fact the claim in the 1st edition was correct. So he made an error in thinking that he was correcting himself. He had it right to begin with. And so, yes, it's exactly the same as the story about the epidemiologist. But it's interesting. We'll see where this error arose, and this will help to also understand path to motivation for SWIGs. So Pearl lays out how he came to the conclusion that this independence held. It did not hold. Okay, so he looked at this. Y of A, B independent of B given Z and A equals A. So Pearl's approach, this also shows to you the alternative approach to linking graphs and counterfactuals. Pearl makes copies of the graph. He makes one copy of the graph. This is the original graph. This is the same graph we had before. I've just turned it to make it look, this is the way that Pearl originally presents it. he makes a copy of the graph, the actual variables, and then another copy of the graph when we intervene on A and B, and then they're then linked together by the error terms for variables that have not been intervened on. Okay, so we have an error term for Y, an error term for Z, and an error term for H. Okay, and Pearl says, well, he looks at this independence and says, Y of A, B, and B conditional on Z and A equals A. And he says, well, look, I've got this path, Y of AB, Z of AB, H of AB, UH, HB. Okay? I've got a deconnecting path. If I have a deconnecting path, that would suggest that this independence doesn't hold, right? But actually, there's a slight subtlety here, which is that this graph here has variables that are deterministically related. Okay? In particular, by consistency, when A is equal to little a, then this guy Z will be equal to Z of AB, because Z of AB is equal to Z of A. Because B has no effect on Z, so Z of AB, that's the value of Z when I intervene on A and B. Because B has no effect on Z, this is equal to Z of A. And so when A is equal to little a, by consistency, Z will also be equal to this. So consequently, if I condition on A equals little a and Z, then I also actually know this value over here. Okay? And that blocks this pathway here. So what's gone wrong here is that once we have variables that are, this is a well-known problem with deconnection, which is that the completeness results of deconnection assume that we have variables that are not deterministically related. Here, when I make these two copies of the graph, I have variables that are deterministically related. So basically, Pearl's excellent tool, D-separation, which is the tool that we use, the crank that we're using all the way through in these swigs, Pearl's tool is not quite so effective when it's applied to this twin network because of these deterministic relations. It should be said, Pearl is also doing something more ambitious. He's trying to represent a joint distribution over a larger set of variables, an unidentified set of variables, and a set of variables that have deterministic relations. We're setting our ambitions lower. We're not putting Z and Z of AB on the same graph, but the plus side is that we then get that for all the graphs that we construct, we have completeness holding amongst the variables on the graph. So if we construct a swig and we see a deconnecting path, then we know that there exists some counterfactor distribution in which that independence does not hold. I should add that Spitzer and Pearl, Ilya Spitzer and Pearl, introduced a pre-processing step to try to address this point, whereby you first draw this graph and that you then start combining nodes based on the particular variables you're conditioning on. So there is a workaround, but the workaround is quite complicated. Okay, connecting us back to the do calculus. So factorization of modularity is sufficient to imply all the identification results that hold in the do calculus. So basically, this quantity will be identified if and only if this quantity will be identified from the swig. Okay. Let me briefly just say we can also use these graphs to do dynamic regimes. So a dynamic regime is a policy that assigns treatment, usually at multiple time points, on the basis of past history. So, and it could even be depending on the natural value. So for example, exercise for as long as you would have done without intervention, or 20 minutes, whichever is more. So here this is now extending the representation to include a situation where I'm now not considering a counterfactual world where I fix A1 and A2. I'm now considering a counterfactual world where A1 and A2 are assigned by some possibly random process that could even be depending on what your natural value is, as in this case. So, exercise for as long as you would have done without intervention, or 20 minutes, whichever is more. So the value that you're assigned under this protocol depends on how long you would exercise. Okay? So Jeff, who exercises always more than 20 minutes, he is going to just be left to exercise the amount he would naturally. If I exercise less than 20 minutes, I'm going to be forced to get up to at least 20 minutes. Okay, so to conclude here, the strength of these graphs are that I think they eliminate a false trichotomy. So previously, the only approach to unifying counterfactors and graphs was the approach described by Pearl, and that was via non-parametric structural equation models with independent areas. And for reasons that I can go to over in the question and answer, that is quite a strong assumption and is not empirically testable. So causal modelists have had three options. They could use graphs and not counterfactors. If they didn't like this independent area assumption, they could just say, I'm happy with graphs, I'm happy with causal Bayesian networks, I'm happy with the do calculus, I'm not going to use counterfactors. But in doing that, they divorce themselves from this large statistical literature that does use counterfactors. Or they could use counterfactors and not graphs. There are many biostatisticians who that's true of. Okay? Who just say, I'm not going to use graphs because as soon as I use graphs, I start having to make all of these assumptions. Or they could use both graphs and counterfactors, but then they're forced to make a lot of additional assumptions, and those assumptions are not experimentally testable, even in principle, and they're not necessary for most identification results. So all of the do calculus results that, for example, do not require these extra independence assumptions that come in once we assume areas are independent. So the SWIGs show that one can use graphs and counterfactors without being forced to take on additional assumptions. This isn't to say you shouldn't ever make those additional assumptions. You're free to do so if you think that they're useful, but we don't have to have arguments. If there are two groups and we're both interested in results that don't need those extra assumptions, we don't have to argue about whether or not those extra assumptions hold. So some summary and extensions. This provides a simple way to unify graphs and counterfactors via node splitting. It works by linking the factorization associated with the two graphs. It represents a counterfactor distribution that's identified from the distribution in the original DAG. This provides a language that I hope will allow counterfactor and graphical people to communicate without having to worry about making untestable assumptions. Two things I haven't covered. It provides a way to combine information on the absence of individual and population level direct effects. So sometimes you might know that there's no direct effect because you have a randomized experiment. So you know on average there's no direct effect. At other times you might have in detail knowledge, you might know that the stuff really does nothing, that there's no one of type helped or hurt. And also another point that I went back to before, the SWIGs allow us to formulate models where interventions on only some variables are well defined, which, as I said, was a problem with non-parametric structural equation models. And I'll stop there. And apologize for not taking a break earlier.
I have a question. So you told us of all of the nice properties of SWIGs, and I was wondering. I mean, a lot of the examples that you were giving, particularly at the end, were models and instances that were sort of hand formulated by, you know, in some sense, the scientist and the epidemiologist. And I was wondering, whenever the domain gets quite complex with perhaps hundreds of variables or thousands or maybe even millions of variables, how would one sort of utilize this, in particular in an automated fashion?
Okay, so in some sense I just have to say, I will say there is a, so I don't really have time to answer that question in great detail, but there is I have the part of the talk that I didn't get to. So I just give you a little snapshot of one bit of it. Rather ambitious. So there are algorithms that can learn graphs from, I mean, structure learning algorithms that can learn graphs from observational data under certain assumptions, and what's going on here? Here we go. Yeah, so So in some sense, so how many of you have heard of the PC algorithm or the GES algorithm? Okay, so that's an algorithm that takes in data, it makes faithfulness assumptions. So the mathematical problem given there is I'm given a distribution that factorizes according to an unknown DAG and a distribution over observable variables that satisfies the faithfulness assumption, and then what can be inferred regarding a structure of G. So that's a graph learning algorithm, and those have been run, those have scaled up to, I don't know about millions of variables, but certainly thousands of variables. How reliable they are does tend to depend on how much data you have and how. And there are many other, I should add, there are many other approaches that are now being used that are not non-parametric, that make certain kinds of parametric assumptions and that can even learn more about the structure under those particular parametric assumptions. A problem that has interested me greatly has been what can we, as you sort of tell from the graphs that I went through, I'm often worried about the possibility of confounding. I really don't want to assume that there is the absence of confounding unless I have very good reason to do so. And so I've spent a lot of time thinking about the situation where I have a DAG, but I only get to see some of the variables in the DAG, and I'm not willing to make assumptions about the number of hidden variables or their state spaces. So things like applying the EM algorithm are then not directly, can't be applied directly. And there are algorithms that can learn something about the structure of a DAG with hidden variables. And this was a recent paper 2 years ago where we tried to speed up this particular algorithm, the FCI algorithm that was due to Spertis et al. Back in 1993. And you can see, it does run. It was possible to get it up to running on 500 variables we were running. And actually, since then, we had a bottleneck here, which was that the structure search involved, it could was not necessarily polynomial time even on sparse graphs. And since then, new work by Klassen, Moy, and Heskes has come up with an improvement on that algorithm that does run in polynomial time on sparse graphs, so it's even more practical.
So are there other questions? Because if they're not, I have another question. So actually the very last bullet point of what was not covered, you talked about when intervention was not well defined on all the variables. Yeah. And I was wondering if you could define what you mean by not well defined.
Yeah, so basically this is just a circumstance. So, if we have a circuit, if I have a set of equations describing a circuit, then it's perfectly reasonable to think about intervening on every particular, removing each one of those equations. But there are plenty of examples where people will have variables. The simplest one, as I said, was where one of my observed variables is my response to a question. There are ways to make people say certain responses to a question, but it does get pretty, it does get into the realm of science fiction to think about that. I mean, one of the advantages of the potential outcome framework, I think, is that it does make people think very hard about what they really mean by their intervention. So if there are lots and lots of studies where people look at the effect of an extra year of education on income, and many efforts to estimate that particular effect. But we can see, if we think about it, it's not enough to just say I'm going to increase the level of education by 1 year, right? There are many, many different ways you could implement a policy to increase education. You could, send people to preschool a year earlier. You could send them to kindergarten a year earlier. You could force the leaving age to be 1 year more than it is. You could round people up and send them to re-education camps for a year. I mean, there are a lot of different ways you could make that particular intervention, and each one will have a very different policy outcome, policy profile. And a lot of statisticians who see people write down graphs and then immediately just talk about crossing equations out and writing numbers in, say, well, in my particular specific context, I want you to tell me how that's well defined or how I could possibly learn about that.
take a break and let's thank Thomas once again. Thank you very much.